In this video, we're going to look at the binomial expansion. In previous videos, we've looked at the binomial expansion for positive integer values of n. An example might be the quantity 2 plus x to the power of 4, or the quantity 1 minus 3x to the power of 6. For these, we use the binomial theorem to find a finite expansion with n plus 1 terms. So let's look at an example. Let's say we had x plus y to the power of 3. 3 is a positive integer value. This gave us now x cubed plus 3x squared y plus 3xy squared plus y cubed. So we can see now that n is 3, which is a positive integer, and then we've got n plus 1 terms. So if this now is a positive integer value, then we're going to have a fixed number of terms, and that's simply 1 more. So if this was 4, that would be 5. In this video, we're now going to extend this on and look at an infinite series expansion when n is a real number, but it's not a positive integer. So that's going to be a rational number. It might be a minus value, or it might be a fractional value. So an example of that might be 1 plus x to the power of minus 6. It might be 2 plus 3x to the power of 1/2. It might even be now 1 minus 6x to the power of minus 3 over 2. These are all now rational indices, or a rational index. If we have this case, we can write out now the binomial series is 1 plus x to the power of n, and that now is equal to 1 plus n multiplied by x plus n multiplied by n minus 1 multiplied by x squared over 2 factorial. 2 factorial is just 2 times 1. Plus n minus 1, n minus 2. Then we have now x cubed over 3 factorial. 3 factorial is just 6. It's 3 times 2 times 1. Plus ... and so on and so forth. This is what we call an infinite series expansion, and is only valid when the modulus of x is less than 1. And any time we're dealing with this, we need to state this. This is now a convergent series if and only if now x is between minus 1 and positive 1. If we look at this now, in terms of the expansion right here, the proof of this is beyond the scope of the course, and also its convergence. What we're going to do though is just consider now if this was 1/2. That was a half, that's a half times minus a half. A half times minus half times minus 3 over 2. A half times minus half times minus 3 over 2 minus 5 over 2. You can see now that that is going to continue indefinitely. It will converge now if x is between minus and positive 1. So what we're going to do is go back a bit and look at something that you might recognise. So what I'm going to do is look at the series expansion, the infinite series expansion of 1 plus x to the power of minus 1. So if we consider now expanding this, what we're going to have now is 1 plus n, which is going to be minus 1, multiplied by x. Plus now n, which is minus 1, multiplied by n minus 1, which is minus 2, multiplied by x, which we need to square. We now need to divide by 2 factorial. I like to multiply by 1/2. The reason being, if we have any fractions in this part right here, it just looks a little neater if I'm simply multiplying by 1/2. Fraction now here in the numerator just looks a little messy. Plus minus 1, minus 2. So n minus 1, n minus 2, which is minus 3. Then we'll have x. We will cube this now and divide by 3 factorial. 3 factorial is 6, so we'll have this. Plus ... and so on and so forth. We show now that the series continues by putting an addition sign and 3 dots. This is what will be expected of you in an exam if you're asked to expand this right here. So let's tidy up 1 minus x. Now the 2's are going to cancel. I've got a minus times a minus, which is positive, so I'm going to get plus x squared. 2 times by 3 is 6. I've got 6. That will cancel. Negative, negative, negative. That's going to give me now a negative. So these now are the first 4 terms in now the series expansion of 1 plus x to the power of minus 1, and we can put this on ... and we can say this is valid when the modulus of x is strictly less than 1. Now if it was 1, let's look what it would do. 1 now, and we'd have now on here, if I put in now minus 1, that would be 0, plus 1, that would be 1, minus 1, that would be 0, and this would oscillate. So we can't say x is equal to 1, the modulus of x is going to be strictly less than 1. Or if you like, now we've got now negative 1 and 1. I prefer this notation. Let's leave this alone for a second. What we're suggesting now is that this will be now a convergent series if now the modulus of x is less than 1 and we expand this out using the binomial expansion. What we're going to do is go back and look at the geometric series and in particular the sum to infinity. So if I write now geometric series, we've studied this in the past, so geometric, we can say that the sum to infinity is equal to a over 1 minus r, where the modulus of r is strictly less than 1. So this was a convergent series now when we had a geometric series and the ratio now was between 1 and minus 1. So let's say we had a first term of 2 and we had a common ratio of 1/2. We could say now the sum to infinity, was a, which is 2, over 1 minus r. So that's going to give me 2 divided by 1/2. We could say the sum to infinity was going to be 4. If we now look at this right here, what we've got is now a geometric series. Common ratio is minus x. So a is equal to 1. The common ratio is equal to minus x. So let's now put this into the sum to infinity. This is by no means a proof. It's certainly not a proof. It's showing one example of how these two things can essentially correspond. So what we've got is 1 over 1 minus the ratio, which is minus x. We know right here that the modulus of x is less now than 1, which we can write just here. And this gives us now the sum to infinity is going to be 1 over 1 plus x. If we rewrite that, we've got 1 plus x to the power of minus 1, and we can see now that these two things are essentially equal. So by no means a proof, but we know that this particular series will converge when the modulus of r is between 1 and minus 1, and we've shown now this way it's going to do exactly the same. And we've got now our binomial series expansion here, and we've shown the first 4 terms. So hopefully that's given you a bit of an insight, but as stated, it's by no means now a proof or anything that you should take more from. Okay, let's look at some of the features. So what we've got then, we know that 1 plus x to the power of n can be written now as 1 plus n multiplied by x plus n minus 1 x squared over 2 factorial plus now n multiplied by n minus 1 multiplied by n minus 2 multiplied by x cubed over 3 factorial, and so on and so forth. This will simply give us the first 4 terms, or those up to and including that in x cubed, plus ... and we see now the modulus of x is strictly less than 1. There's an alternative way we can write this. This will be given in your formula book, but I also like using 1 plus ax to the power of n. If we consider expanding this, we're going to have 1 plus n multiplied by ax. Then we're going to have plus n minus 1 multiplied by ax, which we square and divide by 2 factorial. Then we will have now n minus 1, n minus 2, and we will have ax. We cube this and divide this by 3 factorial, and so on and so forth. So what we can say just here, and I'll write this out twice, we can say that the modulus of ax must be strictly less than 1. Therefore, the modulus of x now will be strictly less than 1 over a. Now, you may ask why I like this. If we had, for example, 1 plus 5x to the power now of minus 3, when we sub in here 5x, we're going to get 25x squared. Often students just write 5x squared. When we sub it in here, we're going to get 125x cubed. Often students write 5x cubed. So this is now an alternative method that you can use. Certainly here you don't have to, but it is an option for you. There's also another quirk. We cannot now use the infinite series expansion when we have a plus x to the power of n. What we do here is take out the factor of a, and we say a to the power of n, and we have 1 plus x over a to the power of n, and we go ahead and expand this like so. So in this particular case, we can say that the modulus of x is strictly less than n. So, strictly less than a. There we go. Okay, so that now is going to be another approach, and we're going to look at some examples of this. As you can probably tell by now, Pascal's triangle is no longer valid when n is not a positive integer. So it's perfectly fine to use it when n is 3, 4, 5 and so on and so forth. But if n is minus 3, n is a quarter and so on and so forth, we can't use it. So let's go ahead and look at some basic expansions. So let's choose some to do. Let's say we've got now 1 plus, and let's go for 1 plus 3x to the power of 1/2. So this is in the correct form. I've got 1 just here. I've got now my ax term or my x term just here. So what we're going to have then is 1 plus n multiplied by x. So this is going to be 1/2 multiplied by 3x. My next term is going to be plus 1/2, and now I need to subtract 1 from this, which is going to give me minus 1/2. I take 3x, I square it, so I'm going to have 9x squared, and divide now by a 2 factorial, which is 2. I'm going to multiply it by 1/2. I'm going to expand this up to and including the term in x cubed. Most exam questions will tell you which to go up to, or they might ask for the first 4 values. First thing I'm going to do before I do that is just state the values of x for which this is valid, i.e. the values for which this infinite series expansion will converge. And we can see from this now that 3x, if we take the modulus of that, that must be less than 1. So we can say the modulus of x will be now strictly less than 1/3. Or if you like, we can say 1/3, we can have x, and we can have negative 1/3 and positive 1/3. So let's just do this term right here, 1/2. I need to subtract 1, so I'm going to get minus 1/2, subtracting another, minus 3/2. I'm now going to take the term 3x, and I'm going to cube that, and we're going to divide this now by 3 factorial, which is 1/6, plus ... and so on and so forth. So as you can see, that's going to go on for some time. Okay, now we would have to show this in an exam. Don't go ahead and just blag it. You must write this out and show it. So what we've got then is 1 plus 3/2x. Also, don't be scared to use a calculator. Often pupils make silly little errors, and one coming up here would be to write that this is going to be 3x squared over 8. Remember, we're squaring this. So positive times by a negative is negative, so this is going to be minus 9 over 8x squared, and be very careful. This one right here, we've got now 6 in the denominator. Yes, we can cancel with the 3 if we like, that's perfectly fine. That would give me 2 and the 3. So in the bottom, I've got now 2 times 2 times 2 times 2, which is 16, and now I've got 27. It's going to be positive, so we've got now plus 27 over 16. So let's put this in over 16, and that's going to be x to the power of 3. Plus ... and so on and so forth. That now is expanded up to and including the term in x cubed. Do not make a mistake. If you want, just put it in. 3 times by 3 to the power of 3 over now. Do put these in. If you've got any doubts, 2 times 2 times 2 times 6. And we'll see now that that comes up to be the 27 over 16. I've got my 2 positive values here. So multiplying, 2 negative values and 2 positives, multiplying them will give me a positive value. So when you're doing this, you need to show all of this and state for which values now of x this is valid. Okay, let's do another one. Let's say that we've got now 4. Let's go for 4 plus x, and we will take this to the power of 3 over 2. We will look now for terms up to and including that in x squared, and we need to state the values for which this now is applicable, or at least it will converge. So the wording is usually for which it's valid. So valid for now which values of x. So this now I need to take the 4 out. So what we're going to have then is 4 to the power of 3 over 2. I've taken that out. That leaves me now 1 plus x over 4 to the power now of 3 over 2. Now if I square root 4 and cube it, I'm going to get 8. So I'm going to get 8, and then we're going to go ahead and expand this. So by taking it out and using rules of indices, I've now got 8. We're going to get 1 plus 3 over 2, so that's n, 3 over 2, multiplied now by x over 4. We're now going to get plus 3 over 2. Now we need to subtract 1, which is going to give me 1 over 2, and we will take now x over 4, and we need to square this and then divide by 2 factorial. So this will be plus dot 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 and so on and so forth. So I'm only doing now the terms up to, and they will say up to and including x squared, up to and including x squared, and state, and I'll just scribble this, state valid x, or the values that make this now converge. So let's go ahead, let's do this. So we've got 1 plus, and then we're going to have 3 over 8x. If we consider this right now, we are squaring this term. So that's going to give me now, if we consider squaring that 16, I've got 8 times by 16. 8 times by 16 is going to give me 128. So plus 3 over 128, and then that will be x squared, plus dot 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 and so on and so forth. So multiplying through, we're going to have 8 plus 3x, plus now 3 over 16x squared, plus dot dot dot. That now is expanded up to and including the term in x squared. We now have to state the values for which this is valid, so we can say that x over 4, the modulus of, will be strictly less than 1, so the modulus of x will be strictly less than 4. Or if you like, minus 4, x positive 4. Again, as stated earlier, I prefer that particular approach. So there we go, that's yet another expansion right there. So we've done one with the half power, we've done one with the power of 3 over 2, and I've taken it out. Let's do now one with a negative. So let's say we've got, let's go for 1 minus 3x to the power, let's go to the power of minus 2, and we will expand this. Let's expand up to term in x cubed, and we need to state valid. So state valid now range for x. So state valid range of x. So let's go ahead and do this. We're going to get now 1 plus minus 2, that is n, multiplied by our x term, which is minus 3x, plus now n minus 1, which is minus 3. Then we're going to take our minus 3x, we need to square this and divide it by 2 factorial. So now I've got minus 2 times minus 3, we're going to square this, which will give me positive 9x squared, plus minus 2, minus 3, minus 4, and then we're going to have now minus 3x, and we are going to cube this. That will give me minus 27x cubed, 1 over 6, dot, 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 and so on and so forth. So let's be careful with this now. 1 plus 6x. If we consider now the 2's are going to cancel, this will be positive. I've got 2 negatives, which will also be positive. So 3 squared is 9, and then I've got 3 times by 9. So this will become 27x squared. Again, if you want to check this, put it through a calculator. Don't make the error. So what we've got then is the following. We've got 2 times by 3 squared divided now by 2, and that's going to give us the 27. This one right here will be positive as well. We can see quite clearly that when I cube this, that will be negative, 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 and negative. At this stage, I can, if I like, cancel 2 and 3 with the 6. Put it through a calculator if you're unsure. 4 times by 27 is 108. So this is going to give me plus 108x cubed, and that will be positive plus dot 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 and so on and so forth. So what we now need to state is the valid interval for x, and we can say that now 3x, the modulus of 3x must be strictly less than 1. So we can say the modulus of x must be strictly less than 1/3. So there we go. Nice straightforward example again. We're using now these values where n is rational but it's not a positive integer. In later videos we'll look at things like approximations. We will look at also working with partial fractions. But for now, hopefully that's given you a good head start. So the take-home messages are as follows. If we have now a value that's not a positive integer but a real value, so it's rational, when we expand this out, so taking 1 plus x to the n, we're going to have an infinite series expansion. We've seen it will just keep going. When this is a positive integer, it will be finite. When we have a value of 1 plus x, for it to converge, we say that the modulus of x is strictly less than 1. We go ahead and expand it out. We consider now the range of values for which x is valid, and we simplify. This is what will be expected of you, and then you'll tidy it up at the end. So in the next video, we'll go through a few examples and then look at some exam style questions.